Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we are going to continue our increasingly epic, now part 5 of our beam column design example. Up to now, we have done load combinations. We have looked at selecting a trial section. We have looked at deflection. We've looked at shear, and we've looked at moment resistance. And now we are going to continue with calculating our compression resistance for this column. If you haven't watched the previous videos, I strongly suggest you should go back and watch them first before you come here. Okay, so let's get started with compression resistance. And this is compression parallel. So we're talking about basically column resistance of this beam column. And, you know, we're checking all these resistances, and I mean, obviously they all are fine because we've checked them against the design tables. Of course, compression resistance for this particular column we couldn't find in the design table because it only went up to a 266 deep, and we are a 304 deep, so we're really going to need to calculate the actual strength is one thing. But the other thing is that when we do our load combinations, not our load combinations, our axial moment interaction equations, we're going to need to have these strengths when we apply those equations. Okay, so recall that the compression resistance is not linearly proportional to KD. So we need to do 3 full different calculations of PR, one for each KD value that we have. The first thing that we need to do is calculate our slenderness ratios. Okay, so let's quickly go back, and now's a good time to remind ourselves what is the restraint condition of this column. Okay, so here's our column, and in the question it says at the top and bottom it's restrained in the out of plane direction. It's restrained in plane in the direction of the floor, so it can't move left and right, and it's also restrained in the out of plane direction at the CLT at the floor location, so it can't come in and out of the page. Okay, so if that was it, then we would have a KL of 1. Not KL. We would have a effective length factor K of 1 for bending, buckling in both directions. So we have buckling in this direction, and we have buckling in the other direction, the strong axis direction. Okay, and we would have basically effective lengths of 1 in both directions. But in addition to those restraints, we have out of plane restraints at the mullion locations. So it is allowed to move in this direction, okay, which is the strong axis direction, but it is not allowed to move in the out of plane direction at those window mullion locations where those loads are. So that means our effective length is going to be 1.0 for weak axis bending only. So for bending out of the plane, weak axis bending, we're going to have a effective length of 1.0. It's going to be KL equals 1.0. Why is it like that? Because if I have restraint here, restraint here, restraint here, restraint here, and I push like this, what's my buckling shape going to look like? It's going to look like this. And each of these has a simple buckling shape that is like a KL equals 1 buckling shape. So the effective length for weak axis buckling is 1.0 meter, but the effective length for strong axis buckling this way is 3 meters because there's only restraints at the end in that case. So we're going to apply that right now when we calculate our slenderness ratios. So let's do CC strong, which is 3.0 meters. So let's say 3,000 millimeters times D, which is the strong axis dimension of the cross section, which is 304. And I get a slenderness of 9.9. Okay, and this is less than 50, so that's okay. Okay, CC weak has a length of effective length So let's remember that this is LE and this is LE. Effective length of 1,000, and the cross-section dimension is 175 in the weak axis, and I get 5.7, okay, which is also less than 50, so that's okay. Now remember, in lumber, I have to check both directions all the time because I have a size effect factor which changes depending on which direction I'm looking at. But for glulam, the size effect factor is based on volume. So basically I can choose whichever one of these governs. And so this is the one that is going to govern the design. So I only have to check basically the column strength for this strong axis buckling. And in this case, the strong axis is more prone to buckling because it has a longer effective length than the weak axis does. Okay, so let's check now our resistance calculations. And I'm going to have to go through this whole process 3 times. So I'm going to keep, I'm going to do each step 3 times as I do them in order to involve each different KD factor in my calculations. Okay, so phi is 0.8. That's fine. Okay, so now our FC, which is our strength, remember, is FC times KD, KH, KSC times KT. Recall as well that FC equals FCB in this case. So we're fine when we go to use these values in our combined axial compression and bending case. Okay, so we're going to do this each time for standard term load. So standard term load, we have our FC is 25.2. Our KD is 1.0, and then we have 1, 1, 1, and we get 25.2. And that is for KD equals 1.0. Okay, then we're going to do the same thing for short term, and we're going to get 29.0. And for long term, we're going to get 16.4. Okay, so now we can calculate our KZCG, which is our size effect factor for glulam, which you'll recall looks like this. I have my volume, negative 0.13 in the exponent. And our volume we calculated before was 0.16 meters cubed, and we get 0.863, which is less than 1, so it's okay. Okay, next is KC, which we get, if you recall, 1.0 plus FC. Okay, where we plug in all these things, this is going to be CC strong now, which was 9.9. Okay, so I'm just going to go ahead and give the final values of this, assuming that you've gone and plugged them in. We have one value for standard term, one value for short term, and one value for long term. So this is K equals 1.0. Okay, so now that I have these different KCs, I have the different FCs, I can go ahead and calculate my PR for each. And the equation is like this. And so I'm going to do that for each. Okay, so now I can compare each of these to the PFs that are associated with each of those KDs, the worst cases. So I had 487, sorry, that's 488. 448 and 210, and this one was 3A, this one was 3B, and this one was load case 1. And they all satisfy, so compression resistance is fine for all the cases. That's compression resistance done. Okay. So now let's look at tension resistance. And you might recall that there was one situation, one load case where we did have some tension. Okay, so there's that one load case that has an uplift force, and the note here is just saying, you know, remember, like, if I do have an uplift force, then obviously I'm going to have to detail a connection that's going to resist that uplift force. That connection is going to have bolts or something. So actually, the strength and uplift might be governed by the connection strength instead of the member strength. But for now, since we're not designing the connection, I'm just going to assume that the full net section is engaged in tension. So I'm just looking at the tension strength of the member as a whole. Of course, when I apply a connection to that member, the overall tension strength is going to go down significantly. But that is thankfully outside the scope of this particular example. So the KD associated with load case 4A is 1.15. Because there's wind. Okay, so there's only one load case that has uplift. And you may recall that for glulam, we have to check FTN. We have to check our net section tension strength and our gross section tension strength. So FTN here is 17.0 times 1.15 is our KD times KH times KS times KT. Then we also have our FTG, which was 12.7 MPa times 1.15 times KH times KS times KT. And these equal 19.55 and 14.6. So let's call that 19.6 and 14.6. Okay, so then I check my TR1, which is my net tension strength, net section strength, AN, 0.9. And AN we calculated when we were looking at shear, and the value was 42,560. And so we get a strength of 749 kilonewtons. And then our TR2. And you see that, like usual, it's our gross area strength that actually governs the 699. Okay, therefore our TR equals our TR2, which is the lowest of the two, which is 699 kilonewtons, which is greater than our TF, which was only 5 kilonewtons. So we are more than fine, no problem. Of course, our connection strength, we're going to have to check against this. Just to circle back on deflection, we can put in our actual E value into our deflection equation and see what the actual deflection is going to be. Once I find it. There we go. Okay, so you remember that our deflection was dominated by the lateral loads when we talked about deflection in the other video. Okay, you'll remember that our delta max was 16.7 millimeters. You recall that our E is 10,300 MPa, and our I is now lost to the annals of time. So if I want to calculate my actual deflection, I have this equation. PL cubed over 648 EI And my P here is my individual load, and that has to be my unfactored load, as you recall, since we're doing deflection, so that's serviceability. So this is 30 kilonewtons. The length is 3,000 millimeters. We're going to cube that, divided by 648. And the deflection that I actually get is 6.8 millimeters, which is quite a bit less, which is less than, I should call this delta, not delta max, which is less than delta max. Okay, so deflection check is fine. Okay, last check before we go to the final load combination check is bearing resistance check. Okay, so let's look at our structure again. What are the bearings I'm talking about here? I'm talking about perpendicular to grain, right? So we're talking about perpendicular to grain bearings. So where is the load being applied perpendicular to grain? It's at these locations here, where the beam interacts with that CLT floor. Okay, I'm not talking about a bearing surface here. This would be parallel to grain, right? So it's just those two red surfaces. They're both 175 wide, like 175 long, sorry. And the beam itself is 175 wide, right? That's the in and out of plane thickness of the beam. So the bearing area is 175 by 175. Did you remember that beam is a 175 by 304? Okay, so, and do we have any loads applied near the supports? No, we do not. The only loads that are applied perpendicular to grain are those two 30 kilonewton loads near the center, and they are not within D of the support, because D is 304, and those are a full 1,000 millimeters from the support. So I'm not going to have to check effective loads applied near a support. I only have to check the effect of all applied loads. And I'm actually haven't provided any bearing data for where the loads are being applied to the beam, so I'm just going to ignore those for the purposes of this example. So I'm just checking where the beam support is. Okay, so we're only going to do the effect of all applied loads check, and our applied load for that is basically equal to the end shear, which is 47.6 kilonewtons. That's our total factored lateral resistance on the beam. So if we go back to our loads like this, you'll see that our horizontal reactions are these loads here, the PE over H. So those are the ones that exist for the dead plus snow. And then for the wind load, we have the same thing. We have this PE over H. And we also have this reaction from the horizontal load, which is 30. So when we add all those up together and we do our load combinations, we are going to get this value of 47.6, which is the maximum value. And that applies to a KD of 1.15. None of the other ones are close. So just like when we did shear, the other ones are like much, much lower. So the KD is not going to, KD gives you 15% more or 35% less. But if something is more than twice as low, then it's not going to govern. So here we have QF equals VF, in this case, 47.6. Phi is 0.8, and as I said, the KD for load case 4, this is for 4D, is 1.15. So there's no KH factor for compression perpendicular. So I just multiply my input value times 1.15 for the KD. And my AB, which is my bearing area, equals 175 times 175. So this is my B here. That's my width of my beam. And this is the CLT length, basically. CLT bearing length. And that gives me Okay, my KB, my bearing, my length of bearing factor is going to be 1.0 because we're at the edge of the member, like we're at the end of the member. And my KZCP is going to be 1.15 because we're bearing on the long face of the glue limb lamination. If you need review of this, you know, go back to the bearing resistance compression perpendicular videos where I explain this in quite a lot of detail. Okay, so now I can calculate my QR. And I get 188 kilonewtons, which is quite a bit greater than my QF, which was 47.6 kilonewtons. So I never looked at my bearing up to now. So it's a good thing that it satisfies the criteria. Okay, I'm going to put one last cut in this. And then in the next video, which is going to be the last part, part 6, we are going to check the interaction between axial load and compression for all the appropriate load combinations. And then we are going to be done.